Hi, in this chapter we will talk about the limit and the continuity of a function and all the theorems that comes with them. So first, what's the limit of a function? We already spoke about the limit of a sequence, saying that the limit of a sequence is a number to which the sequence is headed, and it's approaching this limit indefinitely with all its terms. Okay, now if we take the concept of a limit, the idea of a limit, that we might have a number that we are approaching indefinitely without ever reaching this number. If we take this concept and we try to see if it applies to a function, can we have a function that's approaching a limit indefinitely, and more interestingly without ever touching this limit? The answer is yes. So how to define the concept of limit in the framework of a function? We take f as a function defined on I, taking values in R. So it's a mapping defined on I, and let x0 be in I bar. What's the meaning of x0 in I bar? x0 in I bar, it means that x0 might be in I or might be at the boundaries of I. So it's in the it's an adherent point to I. An adherent point might be an element of I or an element very close to I at the boundary of I, means that if you take any neighborhood around this element, you will intersect I. And let L be a number in R. We say that f has a limit L at the point x0 if for all epsilon positive there exists a number alpha positive, such that for all x in I, if x minus x0 is less or equal than alpha, x minus x0 an absolute value, then f of x minus L is less or equal than epsilon. What does this definition mean? I will read it again. If you take any positive number epsilon, then you can find a positive number alpha such that if x is in the proximity of x0, in the sense that the distance between x and x0 is less than this alpha that you found, if x is in a neighborhood of x0, then f of x is in the proximity of L. It means that f of x is in the neighborhood or in a neighborhood of L of radius epsilon. Let's take it a little bit to the graph to understand what's happening. If you look here, you have a function in blue, this one, okay, and you want to apply the definition of the limit on a point, which is the point in here. Okay, so consider that this function has a limit in here. It means that when x tends to x0, f of x will tend to L. So when x approaches x0, f of x tends to L. What the definition of the limit means? It says that you can choose an epsilon positive, which will be the radius of the neighborhood around L. So if you choose a distance positive in here and positive in here, because it's f of x minus L in absolute value less than epsilon, which means that f of x is between L plus epsilon and L minus epsilon. So if you take an interval around L from L minus epsilon to L plus epsilon, then you can find an interval or a neighborhood around x0 of radius alpha, which is from here to here. So it's from x0 minus alpha to x0 plus alpha, such that any point in here, its image will be in the interval between L minus epsilon and L plus epsilon. So again, if you take a neighborhood around the limit L from L minus epsilon to L plus epsilon, then you create a range such that you can find a corresponding range on x, which is from here to here, such that any point you choose within the x range, so between x0 minus alpha and x0 plus alpha, its image will be within the range between L minus epsilon and L plus epsilon. And the interesting thing is that if you take epsilon smaller and smaller, if your epsilon is very small, so the range around L is very, very tiny, you will still be able to find a corresponding range around x0 such that any point between x0 minus alpha and x0 plus alpha, its image, it will be always between L minus epsilon and L plus epsilon. And if this is true, and if you can do it for whatever value of epsilon you want, then even if you approach x0 indefinitely, the function will be approaching L indefinitely. And in this case, this L, we call it the limit of the function. Now, the limit of the function can be a point where the function is defined. So if you take a point in here, the definition of the limit applies. So if you take a range around this limit, you can find a range around x0, which is in here, such that any point in here, its image is in the range around the limit. So it applies for any point of the function. So any point where the function is defined can be the limit for x approaching x0 at the corresponding x0. Okay, and it's more interesting when the point is not within the domain of definition of the function. Let's take, for example, the case when the function is like this. It's making like this, it stops at this point, and then it continues in here. Okay, so if you take a neighborhood around, if you study this point x0 and you take its image, if you take a neighborhood around x0, can you find a neighborhood around L, sorry, can you find a neighborhood around x0 such that any point in here, its image is between L minus epsilon and L plus epsilon? That's wrong, because a point in here will have its image in here, so it's not within the range of the limit. So if you, in this case, you don't have the definition that applies on both sides of x0. So this is the mathematical definition of the limit of a function. Now, according to this definition, if f has a limit at a point x0, then this limit is unique. And the proof for this theorem is similar to the one with the sequences, but there is a difference because when we are talking about sequences, we had always the n that goes to plus infinity. But in this case, x is not going to plus infinity, which is the input parameter. X can approach a point x0 and can approach this x0 from the right or from the left. So it's a little bit different than the case of the sequences. Let's take a look at the proof of this proposition. Let's suppose that we have a function that has two limits, L1 and L2, and such that L1 is different than L2, and we'll prove that there is a contradiction. Okay, so according to the definition of the limit, for any epsilon positive you choose, you can find an alpha 1 such that for any x0 satisfying x minus x0 less than alpha 1, so for any x in the neighborhood of x0 in a neighborhood of radius alpha 1, then the images f of x will be in the neighborhood of L1, so f of x minus L will be less than epsilon. Okay, and also you can find alpha 2 such that for any x you choose in a neighborhood of x0 of radius alpha 2, this is 2 in here, then f of x minus the second limit L2, this is L2, will be less than epsilon as well. So don't look now at the choice I made in here, 1 over 4 L1 minus L2. I will talk about it later. So we know that if you choose epsilon positive, you can find alpha 1 from one side for the first limit and alpha 2 for the second limit, which means that if you take alpha as being the minimum between alpha 1 and alpha 2, both will be satisfied. I mean, if your alpha 1 is equal to 2 and your alpha 2 is equal to 4, then if x minus x0 less than 4 you have this property, then you have it of course for alpha for x minus x0 less than 2. So if you take the number which is the smallest, 2 and 2, both will be satisfied. That's why we take alpha as being the minimum between both, and then we say that for all x satisfying x minus x0 less than alpha, then it's less than alpha 1 on the first side and less than alpha 2 on the second side. If you take this, you can write L1 minus L2 less than L1 minus f of x plus f of x minus L2, I subtracted and add f of x in order to have the same f of x minus L1 in here and f of x minus L2 in here, then this is less than L1 minus f of x plus f of x minus L2 because of the triangular inequality. And so these two numbers will be less than 2 epsilon, because the first one is less than epsilon and the second one is less than epsilon. Now, if we choose epsilon as being the choice I made, 1 over 4 L1 minus L2, which is positive, of course, then if you take 2 epsilon, it will be something less than L1 minus L2. So why I chose epsilon as being 1 over 4 L1 minus L2? Because I wanted epsilon to be a number such that if you make 2 epsilon, you will stay less than L1 minus L2. So taking this epsilon, you will have L1 minus L2 less than 2 epsilon, which is half L1 minus L2, which is wrong, contradiction. Because you cannot have L1 minus L2 less than half L1 minus L2 strictly. So this is how you prove that you have a contradiction and that the limit is unique. Now, when a function has a limit L that is unique, we say that the function f tends to this limit L as x tends to x0, and we write it limit of f of x when x tends to x0 is equal to L, or f of x tends to L as x tends to x0. We have now other cases when x tends to plus infinity or minus infinity instead of x0, which is a point in R, or when f tends to plus infinity or minus infinity when x tends to x0, which is a point in R, or when both tends to plus infinity. We will try to write the definition in the same framework as the former definition for these cases. Now, if, for example, f tends to plus infinity when x tends to x0, the shape of the function will be like this. It's like when x approaches a point x0, a real number, f is tending to infinity. It's like a function doing like this. So when x tends to a given point x0, from here for example, f of x goes to plus infinity. It means that if you take a positive number as great as you want it to be in here, 1 million, okay, let's say for example, then you can find an x close enough to x0 in here. So it will be an x close enough to x0 in here such that the image of this x is greater than 1 million. Okay, and if you have this condition for all a positive, so even if you take a very, very large, you can still find an alpha which will define a neighborhood around x0. So it will be an interval in here such that any point you take inside, the image will be greater than a that you chose. If this is true, then your function is tending to plus infinity. So for all a positive that you choose, you can find an alpha such that if x is close to x0, so x minus x0 less than alpha, then f of x is greater than a. If f tends to minus infinity, it's the same thing, but f will be less than a negative number b, even if you take b very, very, very small number or very, very negative number. Now, if the interval I has a boundary equal to plus infinity, then you will have x that tends to plus infinity and f of x that might tend to a limit L. This is the case for this kind of function, let's say. If it makes like this and it's approaching a limit L. Then the definition, if we adapt the definition in this case, it will be like this. Even if you take a small interval around L, from here to here, so this is L plus epsilon and L minus epsilon, then you can always find a number a such that any x greater than a, its image will be within the interval L minus epsilon, L plus epsilon. You see? So this is the case when x tends to infinity, f is tending to a limit L. And it's the same that applies when x tends to minus infinity, but it will be on the other side of the axis. If you want to make a definition that generalizes all the definitions, even if you are at a point or at infinity, you might say for any neighborhood of the limit that you choose, you can find a neighborhood around x0 such that for any x in the neighborhood around x0, f of x is in the neighborhood around the limit. And the thing is that the word neighborhood translates into x minus x0 is smaller than alpha when x0 is real, or it translates into x greater than a when x0 is plus infinity, because a neighborhood of plus infinity is an interval of the form a to plus infinity. Now, of course, you can write as well the definition when x0 is infinity and the limit is infinity as well. And it will translate into, for all neighborhood of plus infinity, so for all a positive, you will have f of x greater than a. There exists a neighborhood around infinity such that f of x is greater than a. And here we have a representation also when of the function when it goes to a limit L and when x tends to plus infinity. So this is the neighborhood around the limit, this is the limit L, and then this is the point A from which all the points in here, they have their images between the interval L minus epsilon and L plus epsilon. Now, of course, as you noticed, x can tend to x0 when x0 is a real number, not infinity. X can tend to x0 from both sides. It can come from the right or from the left. That's why we'll define the right side limit and the left side limit. And we say that f has a limit at the right of a point A. So a in here replaces the x0. If and only if it's the same definition for all epsilon positive, there exists alpha positive such that, but here instead of saying that x minus x0 is less than alpha or minus a, which translates into x between alpha plus a and a minus alpha, so we will replace it by x is between a and a plus alpha, which means that x is only on the right of a and cannot be on the left of a. So if x is between a and a plus alpha, f of x minus L is less than epsilon. So the function is approaching L only when x approaches x0 from the right. And it's the same from the left, taking x between b minus alpha and b on the right side. So when a function has a limit L at the right of a point A, then we say that the limit of f of x is equal to L when x tends to a from the right, x greater than a, or we denoted x tends to a plus. A plus is not a number, it's only a notation to say that x is approaching a from the right side. And also we say that it has a limit, a left limit at b when x approaches b from the left, or we say that x tends to b minus. Let's now make an example where we can apply the definition of the limit and understand really how it works. So take the function f of x equals to x2 plus x minus 4 over x minus 1. We will use the definition of the limit to prove that the limit of this function when x tends to 2 is equal to 2. Of course, you might say that f of 2 is equal to 2 because 2 is a point of the domain. That's true. But I'm taking this example only to try to apply the definition of the limit at the point 2, because if f of 2 is equal to 2, then of course the limit of f of x when x tends to 2 is equal to 2. I mean, if x approaches 2, f of x will approach the limit, which is in this case 2. So the definition of the limit states that for all epsilon positive, you have to find alpha. So the problem now is to find alpha. So take epsilon positive, we need to find alpha such that if x minus 2 is less than alpha, then f of x minus the limit 2 is less than epsilon. So watch out, this 2 is the x0 and this 2 in here is the limit. Okay, so the idea in this proof is somewhere similar to the ones we did with the sequences, but the difference is that in there we had always n that tends to infinity, but in here we have x that tends to x0, which is a little bit different. So the idea is that if you want to have f x minus 2 less than epsilon, then you need to find a condition on x. So you need to find alpha such that if x minus 2 is less than alpha, then f of x minus 2 is less than epsilon. So you need to find this alpha, which is the condition on x. You need to make the link between f of x minus 2 and x minus 2 less than alpha. So what you do is that you take f of x minus 2 and you say, in order to have this less than epsilon, what should x minus 2 be? So to make the link, you need to take f of x minus 2 and transform it in order to factorize it or obtain in it a factor equals to x minus 2. So I take f of x minus 2 first, I try to reduce it, I make a common denominator, then I obtain x minus 2 in here. So I put x minus 2 outside, and inside you will have x plus 1 over x minus 1, which can be written as 1 plus 2 over x minus 1. So this is what you obtain. The idea now is then to say that since f of x minus 2 is less than this number, then I need this number to be less than epsilon. And I need to find a condition on alpha so that this number is less than epsilon. So I know that the x minus 2 in here is less than alpha, or it should be less than alpha. Then this will help me to find the link between alpha and epsilon. What I still need to find is an upper bound of 1 plus 2 over x minus 1. This is the strategy that I follow each time. I know that x should be between 2 minus alpha and 2 plus alpha. So if I take, for example, x between 3 over 2 and 5 over 2, this is a neighborhood of 2. You have to take a neighborhood of 2. You have to find alpha, which defines the neighborhood around 2, so that this is less than epsilon, and find the link between alpha and epsilon. So if you take alpha is equal to half in this case, because taking alpha is equal to half, this is 2 minus alpha and this is 2 plus alpha. And you can take something different than half. The important thing that at the end it works. So if you take alpha equal half, what will happen? You will have x minus 2 should be less than alpha, and x will be between 3 over 2 and 5 over 2. And since x is greater than 3 over 2, then x minus 1 is greater than half, then 2 over x minus 1 is less than 4, so if you inverse it, which means that if you add 1, you will have 1 plus 2 over x minus 1 less than 5. So you have this entity less than 5, and you have x minus 2 that should be less than alpha. Then if you take x minus 2 less than alpha, which is less than half, you will have f of x minus 2 less than 5 alpha, which should be less than epsilon. So it's less than epsilon, it's true, as soon as alpha is less than epsilon over 5. Which means that if you take epsilon positive, and if you choose your alpha less than half, choosing alpha also less than epsilon over 5, you will have f of x minus 2 less than epsilon. You put two conditions on alpha. First, you chose alpha less than 1 over 2, and you obtained that alpha should be also less than epsilon over 5. That's why you will take alpha as being the minimum or the infimum between half and epsilon over 5. So the least number between these two numbers. If you take alpha as being the least between these two numbers, then it's less than half and less than epsilon over 5. That's why in this case it will satisfy everything I wrote, and you will have f of x minus 2 less than epsilon. So we were able to find alpha such that f of x minus 2 is less than epsilon for any x satisfying x minus 2 less than alpha. So suppose that you chose in here something different than half, like 1 or 2. You would have the same result. So you will have different estimate in here of alpha, but at the end you will put alpha as being the infimum of all choices that you have made between the thing that you obtained with epsilon and the thing that you chose at the beginning, and then you will be done. Take now another example when x tends to a finite number, and in here it's to the right of 1, and f of x tends to plus infinity. It means that if we take a positive number a, we need to find alpha, which will define a neighborhood around 1, and in this case the neighborhood will be on the right of 1, so between 1 and 1 plus alpha, such that f of x will be greater than a, and this is the definition of the limit at plus infinity. So we have f of x equal to square root of x minus 1 over x2 plus x minus 2, which is the definition given in here, and which is equal to, if we factorize what's in the denominator, we'll obtain at the end 1 over square root of x minus 1 times x plus 2. So we need this to be greater than a, right? So we have to make a choice for alpha. If we take, for example, alpha less than 1 in this case, but you can take other choices, it's not a problem at all. If we take alpha, for example, less than 1, then x being less than alpha plus 1 will be less than 2, which means that x plus 2 will be less than 4, and 1 over x plus 2 will be greater than 1 over 4. Since 1 over x plus 2 is greater than 1 over 4, then f of x is greater than 1 over 4 square root of x minus 1. Why we found a lower bound of f of x? Because we need it to be greater than a. So we say that if this should be greater than a, then what alpha should be? Then 4 square root of x minus 1 will be less than 1 over a. Then square root of x minus 1 will be less than 1 over 4a. Then x minus 1 will be less than 1 over 16a squared. And this is what should be less than alpha. So x, since x is less than alpha plus 1, then x minus 1 will be less than alpha. So this should be less than alpha. That's why we choose alpha as being less than 1 over 16a squared. So alpha will be in here. So if x minus 1 less than alpha, then x minus 1 of course is less than 1 over 16a squared. So x minus 1 less than alpha, then it's less than 1 over 16a squared. Square root of x minus 1 is less than 1 over 4 alpha, which means that 1 over square root of x minus 1 is greater than 4a, then f of x is greater than a. So how did we choose the 1 over 16a squared? We did the calculation on the scratch, if you want, on a scratch paper, to see what choice should we do to alpha in order to have f of x greater than a. So finally, choosing alpha as being the minimum of the choices I made, which are 1 and 1 over 16a squared, I will have for all x between 1 and 1 plus alpha, f of x greater than a.